So from this lecture, I will just cover 2 or 3 slides, okay, just to make sure that everyone understand the very important and basic level of layering and encapsulation concepts, okay, and then we'll move forward to the application layer and the topic of DNS, okay. Is it our class? Not our class, okay. Um, right. So in fact, to the slide, yes, where these this is the current implemented the internet protocol stack, the TCP/IP layered architecture. Okay, so application, transport, network, data link, and physical layer, and this is the boundary where there were two more layers being presented by the being being put forward by the OSI model. Okay. Which were the presentation and session layer. So now I'm going to put a question in front of you guys. Uh, why presentation and session layers were not able to make place in the actual implementation of internet layered architecture, the TCP/IP protocol stack? Why was that? I mean, were those layers redundant? Their functionalities were already provided in somewhere else in the protocol stack, or those layers were unimportant, something like that. Today is 1 hour or 2 hours? Okay, good. Yes, anyone? Because it's part of operating system. Sorry. Because it's part of operating system. Bilal, yes. Uh, which portion of presentation or session layer is part of operating system? By the way, by the way, your application layer and your transport layer is also part of operating system. Okay. TCP and UDP, they come as an implementation inside your operating system. Okay. So right. In the seven layer model, if we think in this way, in the 7 layer model, application, presentation, session, and transport all will be part of the operating system. So that is that may be a correct answer partly, but I'm looking for something else. First of all, before answering that question, yes, again, you are moving. Your answer is in the right direction. Before answering that question, let's put another question in front of us. What are the functionalities of presentation and session layer? Because based on those functionalities, we will be able to answer why they were not part of the original protocol stack. So in the next slide, it is shown here that the presentation layer allows application to interpret meaning of data, for example, encryption, compression, these things, and the session layer is responsible for synchronization and recovery of data exchange and things like that. Okay, these are the functionalities. Why it Yes. Okay. Abdullah, thank you for the answer. Again, right answer. So the point is the way internet protocol stack got implemented. These two layers were not able to make their space in the protocol stack as a separate layers because there were no separate protocol forward because sometime in my introductory class, I say 1 or 2 sentences. A course on computer networking is a course on the layered architecture of internet. Okay, and another way of saying it, this is that a course on computer networking is a course on the networking protocols. In fact, throughout the whole course, you keep studying the networking protocols. For example, at application layer, you have file transfer protocol, okay, FTP, you have SMTP, simple mail transfer protocol, you have HTTP, hypertext transfer protocol. At the transport layer, you have TCP and UDP. At the network layer, you have the SOL, very, very important protocol, the glue that binds internet together, IP, internet protocol. At the link layer, you have Ethernet, Wi-Fi, PPP, ATM, things like that. And then at the physical layer, you have fiber and other protocols, X.25, things like that. So with the advancement of internet, there were no real protocols which were important enough to be made part of the protocol stack. So, for example, where, in a couple of slides, when we will see the layering and encapsulation concept of the packet, how packet is being formed and headers and control information are being attached. There were no layers which perform the functionalities of presentation or session, and their protocols were already there at the early part of the internet, and they attached their headers. So obviously, the way internet evolves, it evolved without these two layers. Then when the internet became a public commodity, at that point, the need was to implement the functions of presentation and session layer. Then how the internet community reacted, the way they did is that to implement the security, the encryption, the functions inside either application layer or transport layer. So that answer from Abdullah and from Waqas is correct, that you need to implement these functionalities yourself. The functionalities are not redundant, the functionalities are important, but because the way internet evolved and because the way important protocols are put forward at the early stage of the internet history, these layers didn't came part of the actual protocol stack. Okay, but for example, the most important functionality of application layer, security. These days, TCP includes security as a feature of SSL. As this is one of the enhancement of TCP. You know, TCP enhanced with SSL, and for example, HTTP. Then when collaborate with it, not with traditional TCP, but TCP with SSL, HTTP becomes HTTPS. And if you have noticed on many websites, you have noticed there is a green lock on the address bar of the website. This includes that particular website is not an HTTP, but it's on HTTPS, which means that the TCP version it is using is enhanced with either TLS or SSL, secure socket layer. So this is not the actual implementation of TCP, the traditional implementation, but it is an enhanced implementation of TCP. So this means the long story short, the presentation and session layers, their functionalities are important, and if you need those functionalities, either the application programmer have to give those functionalities at the application layer, or the transport layer protocols like TCP or UDP have to include those functionalities by extending or enhancing their traditional versions. Okay. Now I just want to show one more slide.
Excuse me, sir.
Yes,
I think you forgot to share your screen because we cannot see anything.
I am so sorry, but you guys are so late to point out that. Okay. Yeah, I did forgot. Okay. Okay, now I will flash those two slides again, but they are very trivial slides. You can see the screen now, right? These are the 5 layers.
Yeah.
Okay.
Yes.
Application, transport, network, link, and physical. Okay. So whatever discussion we have done until now, no damage done. Hopefully, the screen was not that important. The what I was talking about was more important. But this is the comparison we were talking about. We were talking about this comparison of the actual TCP/IP protocol stack versus the OSI model, which included the presentation and the session layer. Okay. But the discussion was clear, right? So I was audible, so you were able to hear out what I was saying. Okay. So these functions, encryption and security and error handling, these are important. But these functions are now included either in the application layer or in the transport layer. Okay. And thank you for pointing it out. Okay. So Internet Protocol Stack is sometimes presented in this way, and we call this concept as the narrow waist. Because the waist is being narrowed over here. This is a very common term being used in the research papers and in the networking community, and they call this concept as the protocol stack is being presented like this, and the waist is narrow over here because on the upper layers you have many protocols, on the lower layers you have many protocols, but in the middle layer, which is the network layer, you have only one protocol, which is the IP protocol, the internet protocol, and IP is the glue that binds internet together. Okay. So each and every device running on internet must have an IP address and must run IP as protocol. Each and every device. Okay. So and obviously on the top layers we have application and transport. According to the OSI model, you can say this as 5. The application is, you can say it is number 5. Okay, something which is depicted over here. So the application and transport, you have many protocols over here, you have many protocols over here, but in the middle you have only IP. Okay. This I want to show you guys, and um, I've shared the since I've shared the desktop, so the PPT should also be visible. It's the same slide from Cross and Ross, but I want to show it in PowerPoint so that the animation is clear. Okay, static slide. So I just want to show the process uh, once to show everyone how we have covered most of these slides. This is one of the last concept that we are going to cover before moving to chapter 2, application layer. Okay. So in this simple example, we will run through the concept of encapsulation, and it's going a little bit out of the our projector screen, but you guys can see, right? It's clear. Okay. There is a switch over here. Okay, and it is being shown as a layer 2 switch. Okay. Okay, the protocol stack being built with this switch is comprised of layer 2, physical, and two layers, physical and data link. Okay, and this is a router. It's obviously always a layer 3 device. A switch can be a layer 2 or a layer 3 device. Okay, a switch, traditionally switches were meant to be layer 2 devices, but now we have packet switches. It is very common. Okay, we have packet switches which are layer 3 devices. So the term switch is being used, but they are called as packet switches. So they have the understanding of IP addresses as well. Okay, so their protocol stack or their layered architecture, layered understanding will be something like that. Okay, but the switch being shown in this diagram is a layer 2 switch. Okay. Okay. We have source over here, and the source and destination, the end systems, the edge of the network. We discussed the network segments in this chapter, right? The edge, the access, and the core. Okay. So the edge of the network, which are only the sources and sinks of the internet. Okay. The end systems, or either servers or data centers. Okay. So over here we are showing two end systems. Okay. One this one, and another one is this one. Okay. So the edge of the network always have a complete protocol stack. Okay, remember this, please. Okay, याद रखिएगा. The edge has the complete protocol stack. Okay, so we have physical, data link, network, transport, and application layer, and it is partly implemented in software and partly in hardware. So the application layer, transport layer, and the network layer, these are part of your operating system in modern day internet, at the edge of the network. Okay, these are part of your operating system, or your mobile operating system, or your any gadget that you are holding in your hand. Okay, it is part of that software. Okay, and the link layer, it is partly hardware, partly software. Okay. Okay, so the link layer, the protocol part of the link layer is software based, so the Ethernet, the Wi-Fi, and the other part, which is in the NIC, the network interface card. Okay. Okay, you the NIC, you have all the NICs in your devices, right? In the fixed PCs, in your laptops, and in your mobile phones as well. Okay, so you have a network interface to support your Wi-Fi, or in the case of mobile, and in the case of laptop or PCs, Wi-Fi or wired internet. Okay, so the NIC is the hardware part of your data link layer. Okay, so this whole protocol stack is implemented in the edges, and then you have devices in the middle who have part understanding of the part of the protocol stack depending on their capability. So a layer 2 switch understand until layer 2, and a router or a layer 3 switch understand until the network layer. Okay. All right. So how this encapsulation will take place? So we studied one sentence a couple of lecture ago when we were studying the network core, and we said when we were studying the difference between the circuit switching and packet switching, we made a statement that the application layer divides messages into chunks, which are then brought down the stack, and became packet after headers being attached by each layer. Okay, so we are going to follow up on that statement with this example, and let's see how encapsulation is being done. So you can see here that the application layer has a message. It's called message over here. And by the way, the jargons that I am using in this slide, and obviously in throughout my whole course, are the jargons being adopted by the textbook Cross and Ross. Okay, you may find some difference in the jargons being used in other books or research papers. So by the jargons, I am talking about the name of the data. The data is called as message at application layer. It is called segment at transport layer. It is called datagram at the network layer. It is called frame at the link layer, and it is called bits at the physical layer. Okay, these are the jargons being used by the book K&R. Okay, which we are right now following, at least in the first 50-60% of the course. Okay, before moving to the advanced topics. So these jargons, I mean, you should know. For some books will call at the network layer as packet. So segment and then datagram. Some books will call this as packet. So I mean, the Cross and Ross use packet as generic term. So when the book says packet, it means it is not talking about any particular layer. But when it says segment, immediately in your mind, transport layer should come into the play. And when it says frame or datagram, so that particular layer comes into play. Okay. Okay, so what's the message? It's the application layer form of the data, and then it goes to the transport layer, and the header of transport is being attached, and then it becomes segment. Okay. For each preceding layer, the payload is the data being forwarded by the previous layer. So for segment, for transport layer, message is the payload. For network layer, this is the payload. Okay, this over here. This is the payload for network layer. Payload is something which is being provided to you, and then you attach your header to the payload. Okay, so payload is coming from the upper layer. Okay, so for transport layer, message is the payload, and then its header is attached, and it becomes segment. And for network layer, segment is the payload, and then its header is being attached, and it becomes datagram. And for data link layer, datagram is the payload, and then it attach its header, and it becomes frame. Okay, and then the frame okay. This is very confusing. And then the frame appears on wire in the form of bits. Okay. I'm not having a I cannot see the chat window right now. Okay, so there is no chat message. Okay, so let's continue. These are easy things. I'm just repeating to bring everyone on the same page. And this is the most important concept in the whole lecture which I started today. So I just discussed the 5 and 7 layer, and then I'm going to show this encapsulation. Okay. I wanted to say something else before moving forward. Right. Yes. Yes. One more thing before moving forward. Okay. So we studied the jargons. We studied that each. Why do you think that each layer and 4 layers? So transport, network, link, data link, and obviously application layer also has its own header, which is not shown over here because that header is part of the message. Okay. I mean, the application layer in its message and the header becomes the whole message, which is going to be received at the receiver end. Okay, the application layer of the receiver end. Okay. So, for example, if it is a web browsing application, then the message will contain the HTTP header and of course the HTTP data part as well. Okay, so that whole thing will become a message. Okay, the question I want to ask is that why so many headers are required in the internet? So why each and every layer has to attach its separate control information? Transport layer attaches its own separate header, its own control information, which is going to be detached by the next transport layer. And by the way, transport and application layer only resides in the end systems. I repeat, transport layer and application layer only resides in the end system. You cannot find transport layer and the application layer in the middle of the network, which means that only at the source and only at the destination you will find transport layer and application layer. Okay. So the transport and application layer, routers and switches, they don't have any understanding of those layers. Okay, in principle. We will discuss the points during the course when this is violated. That's the principle of internet. Okay, and to put this principle in words, you can say the core design principle of internet is complexity at the edges. And another way of saying it is keep the core simple. Internet has already a very complex core. Okay, so packet switches and routers, they have to process, I mean, core routers have to process, thousands of packets per second. So if you are going to say to them that you should have an understanding of the transport layer as well, the TCP and then the application as well, this is putting a lot of burden on them. So if you want to keep the core simple and put the complexity at the edges, the transport layer and the application layer will only reside in the end system. Okay, so an encryption or a compression once done, it will not be decompressed or decrypted in the intermediate nodes by any router or any switch. Okay, it will not, these things will take place at the other end, at the other edge of the network. Okay, the destination. These are all very important concepts. I know basic, but very important. So so I'm going to put the question I asked you guys: why so many? Why each and every layer need to attach its own separate control information like that? Transport layer attaches its own separate control information, then the network layer, then the data link layer. Yes. Every layer is not performing their protocol. Every layer is performing their responsibilities. They are using their, yeah, no, they have to attach it. Okay, but the point where I want to lead you guys is that there are separate set of functionalities being performed by each and every layer. And since all of those functionalities are very important and they are not replicated by the other layers, they are distinctive among the layers, then each layer should have its separate control information as well. For example, what I want to say to you guys is the functionalities. So if you have to, speak the functionality of each layer in just one sentence, let's start from the upper layer, the application layer. Usually, I wanted to write these things on the board, but I don't have, so I'm just going to speak. The recording will be available, but you guys are listening to me. The functionality of the application layer is to provide user interface. And for that, the application layer uses host names. Each layer has its own functionality and each layer has its separate addressing scheme. The addressing scheme of the application layer is host name, www.kickinfo.com, www.facebook.com, coursera.org, cnn.com, things like that. Host name. Okay, and they are, what they are doing, they are providing user interface. The functionality of transport layer is process to process communication, from the correct process on the sending host to the correct process on the receiving host. Okay, and then back. Process to process communication. I used to write these things on board, but you guys are listening to me. Okay, either you can take a note at your end or you can just revisit the recording or just memorize it right now. Okay, process to process, in one single sentence, the duties or the functionalities of transport layer is process to process communication. Okay, there are other duties. TCP perform congestion control, TCP perform reliable data transfer, error checking, error handling, TCP perform flow control. But the most important functionality of transport layer, which the transport layer must provide to the layers below them, the layers above get their functionalities done by the layer below. Okay, remember that. The layers below are providing some functionalities to the layer above. Okay, right? So TCP, so transport is doing what? Process to process communication. But for that, it is getting some functionality from the network layer, and the network layer is doing what? Host to host communication. Okay. So the transport layer is doing process to process communication, and for process to process communication, the transport layer is using what addressing scheme? Port numbers. The transport layer is using port numbers. Port numbers is the addressing scheme of the transport layer. Host names is the addressing scheme of application layer, and it is providing user interface. And transport layer core functionality, process to process communication, and the addressing scheme being used is port number. And then it is relying on the functionality of the network layer. And network layer, what is it doing? Routing. Routing, and routing means what? End-to-end path. End-to-end path means what? Host to host communication. Host to host communication. Okay. And for host to host communication, the network layer is using what? IP addresses. It has its own addressing scheme. Okay. And then the data link layer. The data link layer is providing what? For host to host communication, the network layer require a service from the data link layer. And the data link layer is providing a service of node to node communication. That this is your routing path from one host, from this host to this host, and you have calculated this path. But you want to move node by node, one hop by one hop. So node to node, then node to node, and then node to node. And for that, I will provide data link layer will provide this service of node to node communication, and for that the data link layer uses the addressing scheme of MAC addresses. That is why MAC addresses are sometimes called as layer 2 addresses or physical addresses, because they don't keep changing when you move your laptop from your home to your university or your university to your some other place. Okay, unless you are using a software of poisoning the MAC addresses, that's another thing to do. But in principle, they don't change. Okay, the MAC addresses, they are the physical addresses. Okay, burned inside your network interface card. Okay, while your IP addresses, they may be dynamic. Okay, they keep changing when you move from one place to another place, to which you are going to be connected. Okay, and the IP addresses are also sometimes called logical addresses or layer 3 addresses. So these are all same names of the same thing. Okay, logical addresses, layer 3 addresses, and IP address is the same thing, and physical addresses, layer 2 addresses, and MAC addresses, the same thing. Okay, so this is the whole story. Okay, so now the question gets answered. Why separate control information is required? Each and every layer has a separate functionality to perform, and for that it needs its own header, and the header of those layers will only be detached, decapsulated by their peer layers. So the header of network layer should be decapsulated or detached by the next network layer. And since the network layer and the data link layer, they reside in the middle part of the network as well. So those are the header. Those two headers got detached and detached and detached more often, while the transport layer and application layer only resides in the end systems. So these are the two headers which are sort of sacred information. They are not, they don't get touched by the intermediate nodes. And once they are put, so for example, this is the form, this right here, this segment, once it is being formed, it won't get touched until it reaches the destination, because there are no layers in there are no devices in the middle who have an understanding of, at least in principle, the understanding of the transport or the application layer. Okay, so this header will not be detached. Okay, yes. Physical layer has separate protocols. They don't attach, their headers are from the hardware itself, so in the form of preambles or in the form of some how do you say, yeah, something like that, which not parity bit, but something which shows the start and end of the frame. Okay, which shows that okay, so for instance, your cell phone is communicating, all of your cell phones are communicating with the access point right here. We have an access point in this class, but anyway, in the corridor. Okay, the access point in the corridor. Now the access point is giving all of you turns, so all of your cell phones are sending frames to that. So it has to have an understanding of when one frame is going to be, is going to end and the next is going to be start. So there are some preamble bits at the start and at the end of the frame, which are being used. Those are the you can say that it's not actually a header of a physical layer, it's actually a trailer of the data link layer. So the physical layer, they don't put it's just a communication medium, the way the information is being represented on the link. Okay. Data link layer is the only layer, ये वाहिद layer है, okay, uh, which attaches header as well as trailer. It is not shown here on the slide, but the data link layer do attaches trailer as well, because it has to show the next hop, the start and the end of the frame. Okay, so there has to be a sequence here, and there has to be a sequence over here, which shows the start and end of the frame. When we will study the data link layer, we will see that Ethernet and Wi-Fi, they have header and trailer both. Okay, so there is some control information in the header, including MAC addresses and some things like that, and then there is some control information at the trailer as well, which shows that now the frame is going to be at, and be prepared to receive the next frame, which again will have preamble at the start and at the end. Okay, we are
Yeah,
jumping
so
forward. This we will study.
excuse me, sir.
Yes, please.
Yeah. So the header of, for example, network layer will keep being a tad and DTAD until it reaches the destination.
Yes, let's move forward in the slide, and you will see here. So if you notice, you see now the it's not shown in the simulation. Anyway, at this point, yes, your question is that, sorry, I interrupted you. The question is that the network layer header and the data link header and trailer are going to be attached and reattached in the intermediate nodes. The answer is yes. Okay, it's not being shown here in the simulation, but when this packet arrived over here, it will move forward. It will move down the protocol stack. The network layer will detach its header, and then the data link layer will detach its header. Okay. Uh, okay. So no. It's shown over here. I think right now the header of yes. Okay. It's shown over here. It's shown over here. The header of data link layer is being detached. You see, like this. Or no? Okay, I was just a bit quick in pressing the key on the keyboard. So you see, the data link layer, it receives the frame. You will call it frame, and the it will detach its own header. Okay, it only has the authority to detach the header attached by its peer layer. The peer layer is the data link layer at the previous node. Okay, and it will detach its header, perform some processing. Okay, okay, and then sorry, perform some processing on it. Okay, we will not discuss the processing being performed here, because we have separate chapters of that. Okay, so it will do whatever it need to be done on the on this information. So detach the information, get the content of the information, make its decision. Okay, and then the remaining part will move upward on the protocol stack to the network layer. The network layer will detach its own header. Okay, okay, and then obviously it will reattach the header of network layer again, because now the you're getting my point. Now it has to move again on the wire to the next node. Okay, and then being passed down to the data link layer. Data link layer will again reattach its own header and over here, and headers are being one by one by the all the pairing layers, and then the message is being received by the application layer. Okay. So for example, the most common decision that a network layer can take is based on the IP address, which port to forward. Okay, and the most common decision of the data link layer also based on the MAC layer, which port to forward. Okay, so they both, and these two tables must coincide. But we will study these things in detail. This is what I wanted to show you guys. That's it. But it took time. But these concepts are very important. Let me just show you one more slide of over here of the way the protocol stack is changing. You see, if you notice over here, this is one representation of a protocol stack. Okay, so it's not written like application, transport, network, and data link. Rather, it is written in the form of the protocols being used at each layer. So it is written like this: HTTP, TCP, IP, and 802.11. Okay, so I may ask you that, can you draw the protocol stack of, let's say, I don't know, DNS. So DNS protocol stack is something like that. DNS, and then DNS uses UDP. Okay, so DNS, UDP, IP, and then whatever protocol. If you are on Wi-Fi, then 802.11. If you are on Ethernet wired connection, then Ethernet. Okay, so DNS, UDP, IP, Ethernet, or DNS, UDP, IP, and 802.11. So these are called, these are, you can say that these are the use cases of the protocol stack. And this example right here is the perfect way of illustrating how your cell phone is going to be connected to that access point. For instance, you guys are using internet in this classroom via your cell phone, and you will be doing something like that: HTTP, TCP, IP, and then your cell phone is Wi-Fi. Okay, so 802.11. This will be the real. So this is a specific use case. What we looked in the previous slide was the generic way of saying header of transport, header of network, header of data link. You are getting my point, right? This is a specific use case, and this use case is representing the transmission of HTTP, the web browsing case. Okay, so HTTP header got encapsulated in TCP, its header got encapsulated in IP, and its header got encapsulated in 802.11. Okay, and this portion is being shown in pink, in colored, is because this is the sacred information which will only be touched by the other end system. The transport layer and the application layer, these layers reside in the ends, in the edge of the network. So this information will not get changed. And then your cell phone send this message, this packet to the access point over here. Okay, then the access point, what it will do, if you notice very closely in the corridors, the access point on the front end, they have the Wi-Fi reception, and at the back end they are connected with the CX LAN. So they have certain Ethernet cables going on, going inside the duct. You must have noticed it. You can see in the break in the more closely. So the way, if you notice the way, this is also the beauty of internet, how different algorithm, the different protocols at the same layer are being, um, being interoperable. You understand? Because internet, just like the proverb, Rome was not built in a day, right? There is a proverb, because in Rome, when you go to the next street, there is a building which is 5,000 years ago, and the next street there is a building which is 10,000 years ago, years old. So just like Rome was not built in a day, internet was also not built in a day. So you don't have any homogeneity in the internet. Okay, you have many protocols at layer 2. You have Wi-Fi, you have Ethernet, you have PPP, you have ATM, you have HDLC. You have many protocols at application, at transport. The only homogeneity is at the network layer to bind the internet together. Okay, so because of that, you need devices which must have understanding of both sides of the protocol. So this is an access point of CX in the corridor, and if you notice, it received the 802.11 at IP packet, and it decapsulated the header, and then reattach the headers. But the next hope is what? It's a switch or router in the CX, so it attaches IP and Ethernet. Okay, and then it moves forward, and then it is received at the host, and then detached. So uh, these are all the basic but very important, concepts which I wanted to give you guys regarding layering and encapsulations. Okay, we should take a break of 10 minutes, and let's make it 15. Okay, I've spoken a lot. Let's make it 15. You guys agree, Ji? In the DL mode, let's take a break of 15 minutes. Right now it's 7 in the classroom watch. Okay, I don't know whatever. It's 7 in my cell phone as well. So this is a standard time. So let's reconvene at 7:15 sharp, please. Okay, we'll have the next session of half an hour on DNS, chapter 2, cross and roll. I will stop the recording, but please continue with this meeting, and you can take a break. I will stop the recording right now.